Welcome to the lecture of analysis of several variables. We continue with the module 5, and this is the last topic of the module 5. And in this topic we are going to discuss about the implicit function theorem. So the theorem statement is like that: let omega be open in Rn cross Rm, and f is a function from omega to Rm, which is represented by xy is f1, f2, fm. So since it is going to a functions of Rm, so we have m component be a functions of type Ck, means all the kth partial derivatives are continuous. Now for AB belongs to omega, suppose that f of AB is equals 0 and the Jacobian or the derivative with respect to y variables at the point AB is not equal 0. Then there exists a neighborhood U to A in Rn and open neighborhood V to B on Rm and a function phi from U to V of type Ck such that xy belongs to U cross V subset of omega f of xy is equal 0 if and only if x belongs to U and y is equal phi x. That means the whole expression f of xy is an implicit functions of y. Now what this notation means, that if xy belongs to U cross B subset of omega f of xy 0 if and only if x belongs to U and y equal phi x. By these notations we can interpret that in the neighborhood of AB, if the function f of x was 0, implies that we can write y as a function of x, that is y equal phi x. So therefore, we can say this is an implicit expression f of xy equals 0 and y can be considered as a function of x. If for AB belongs to omega, f of AB is equal 0, which implies B is equal phi A. And third point is that this notation implies, and which is very important and we're going to use later, that for all x belongs to U, f x phi x will be always 0. So this is about the implicit function and its interpretation. So now we are going to use it to solve some example. So here is the problem. First part A is that state the implicit functions theorem. So you have to state it as in state given in the previous slide. And then we have a numerical problem here, that using implicit functions theorem, we have to prove that there exists a neighborhood of U to 0 in R, phi U to R of type C infinity such that phi 0 equals 0 and sine 2x plus 3 phi x is equal to x plus 2 phi x. And then we have to find the derivative of this phi at 0 and first order derivative and second order derivative. So let's start with part B, because part A is statement, so you have to memorize this statement and you have to write it. So let's start with the part B, and for that we consider the function f of xy equals sine 2x plus 3y minus x minus 2y. So when you consider this, you have to keep in mind that we are going to implement the implicit functions theorem. So therefore, we need the that the function f of x satisfies the condition of the implicit functions theorem. The first condition is f of xy should be equal 0. So we got it. F of 0, 0, which is sine 0 minus 0, 0, so which is 0. Next, we have to get the partial derivative. So f of xy equal this. So the expression. So with respect to y, we have to get the partial derivative of this expression. So for that, we calculate it fyxy equal del y sine 2x plus 3y minus del y x and minus del y 2y. So naturally, the x is constant when we do partial derivative with respect to x. So first one will be 3 cosine 2x plus 3y. Second one is 0. Last one is minus 2. So we got fyxy is equal this expression. Now if y00 is equal 3 cosine 0 minus 2, which is 3 minus 2 is equal 1, not equal 0. So therefore, we satisfied the two conditions of the implicit function theorem. Thus, we can apply implicit function theorem, that is, there exists an open neighborhood u to the point a equals 0 and open neighborhood v to the point b equals 0 and the functions phi from u to v such that phi 0 is equal 0 and y is equal phi x. So we prove this one that there is an implicit function y equal phi x. Now from this expression, the note from the last slide that for all x belongs to u, fx phi x is equal 0. So this implies sine 2x plus 3 phi x is equal x plus 2 phi x. So this complete the first part. Second part or part B of the given problem. So now for the part C, we need to take the derivative of the last expression with respect to x two times. So from the first derivative we have here, this expression, if we take the derivative with respect to x, so we'll get cosine 2x plus 3 phi x multiply 2 plus 3 phi dash x, and the right hand side part will be 1 plus 2 phi dash x. Now we have to calculate at 0, so therefore put 0 on both sides, we get it cosine 3 phi 0 dot 2 cosine plus 3 phi dash 0 is equal 1 plus 2 phi dash 0. Now phi 0 is equal 0. So therefore we substitute that and we get it 2 plus 3 phi dash 0 is equal 1 plus 2 phi dash 0. Now we simplify it, we get phi dash 0 is equal minus 1. Now for the second part, we got to take the second derivative of the expression we obtained from the first derivative, and then we use the product rule and we have this expression cosine 2x plus 3 phi x multiply 3 phi double dash x minus the derivative of cosine here minus sine 2x plus 3 phi x, and the derivative of this one is will become 2 plus 3 phi dash x whole square. It is power whole square. So after these simplifications, we will get it here. So at x equals 0, we try to substitute it here. X equals 0, it is cosine 3 phi 0, 3 phi double dash 0 minus sine 3 phi 0, and 2 plus 3 phi dash 0, and that will be whole square. But since here sine 3 phi 0, phi 0 is 0, so sine will become 0, so this will become, this whole things will become 0. And here phi double dash 0, you have to calculate it. And cosine 3 phi 0, again it is cosine 0, which is 1. So therefore we have here 3 phi double dash 0 minus or equal to phi double dash 0. So which further simplification will give phi dash 0 is equal 0. So that's complete the chapter 5. This is the end of the module.